So, some key vocabulary regarding vectors and vector spaces. The last two videos were giant adventures to define what is a vector space, what is a subspace, right? And a vector space in particular is a set of objects that can be added and multiplied by real numbers, scalar multiplication. When you combine these things, that's what you get, what's called a linear combination. Right, so linear combination just means performing the operations of linear algebra, the operations of a vector space. So if you let some vectors be elements of a vector space V, then a linear combination of those vectors, right, of V1 through Vn, is an expression of the form what? Well, what are you allowed to do in a vector space, right? Like we said, you're allowed to multiply by a constant, by a real scalar, right? And you can add them together, right? Those are the two operations that you can do to stay in that vector space V, right? So any expression of the form where those constants come from the set of real numbers, right? So that's what a linear combination is, right? So it's just the kind of expressions that you can have in a vector space, right? You take your vectors, you can multiply by real numbers, you can add them together. That's what there is in vector space. So for a related definition, look at this word span, right? If you take the set of all possible linear combinations, right? That is called the span, right? So if you take all possible linear combinations for all choices of C1, C2 up to Cn, right? That's called the span. Another way to say that, if you want to use set builder notation, you can say span of V1, V2 up to Vn, the same V's as in the previous definition, right, would be what? It's the set of all expressions of the form C1, V1 plus C2, V2 plus Cn, Vn, where the C's are all real numbers, right? So these C's can be chosen across to be any values across the real numbers, right? And then they get, for every possible choice of C, you get another combination, make a set that packages them all together. That's span, right? That's the span. Okay, then, so there we go. There's our next definition, right? So for example, let's look at some examples here. Here's one example. So if you have suppose you have the span of the vectors 1, 0, 1 and 2, 0, 0, right? So you take that, the span of 1, 0, 1 and 2, 0, 0. What is that? That's, so here we are in R3, right? You can see that those vectors are elements of R3. And I have one vector that there's X, Y, Z. So I have one vector, this vector here, right, is what? It's 1 unit in the X, it's 0 in the Y, and it's 1 in the Z. So there's one of those vectors, right? And then I have this other vector, right? I have this vector 0, 0, 2, sorry, 2, 0, 0, right? So that's this vector here, right? So there's 2, 0, 0. And here is this vector 1, 0, 1. So there are the two vectors, right? And then what's in the span? Well, it's the set of all linear combinations of those two vectors. So it's everything of the form c1 times that first vector plus c2 times that second vector, right? Where c1 and c2 can be any real numbers. Okay, so now think about, what does that look like? What kind of points does that generate? Well, I can get this point by taking, c1 equal to 1 and c2 equal to 0, right? I could take this point, right, by taking c1 equal to 2 and c2 equal to 0. I can get this point by taking c1 equal to 3 and c2 equal to 0, and so on, right? So I can get that whole line by making c2 equal to 0. I can do the same thing along the purple line, right? I can get that whole purple line by taking, I could do this, say that location right there, by taking c2 equal to 2 and c1 equal to 0, right? But then I can also mix and match these, right? So say I did one of each, right? So 1 c1 and 1 c2, and I end up there at that point, right? So this will be at the point 3, 0, 1, right? That's what I get if I take one of each, right? And so with playing around a little bit, you can see what kind of points do you get. Well, what does this give you? This gives you the whole xz plane, right? You can reach using those two vectors, right? Using fractional amounts of them, negative amounts, right? Mixing, matching, however you like for any real number, c1, c2, you can reach any point in the xz plane, right? Another way to say that is it's the set of all points x0, z, where x and z are in the reals, right? That's another way we can say that. So there we go. We just calculated a span, right, in R3. So the span of those two vectors, right, ends up being that whole xz plane. All right, so that's an example of a span. So what is linearly dependent and what is linearly independent? So here's the idea. Suppose I was going to toss another vector into this span. Suppose I wanted to consider the span of 1, 0, 1, 2, 0, 0, and 3, 0, 1. Right? Say I toss the vector 3, 0, 1 into that list of vectors, and I consider it along with the first two when I calculate my span. So now, by definition, I have all linear combinations of these three vectors, right? Okay, well, it looks like I have more than before. If you just look at the notation, right? Now I'm adding up three vectors instead of just two. Okay, but this 301, we've seen that before. That was just a linear combination of the first two, right? 301 is just a 101 plus a 200, right? Okay. Well, now you could do a little bit of distributing and combining like terms. Well, that's just C1 plus C3, 101. And C2 plus C3, 200. Where C1, C2, and C3 are all real numbers. Ah, okay. Well, now you could actually rename C1 plus C3 as just C1. And you could rename C2 plus C3 as just C2. Now we're back to the old span, right? So we tossed that new vector in there. We didn't actually get anything new in our span, right? It's the same span as before. We're back to just those same two vectors by doing this little bit of algebra, right? Geometrically, how can you think of it? Well, see now we added in this third vector, right? But that third vector, see, we had the purple vector, we had the blue vector. Oop, blue vector. And now this green vector, when we added that in, this green vector, this was already contained in the plane that the first two generated. Right? The plane that was spanned by the first two. Right? So it didn't give us anything new. That was already a point that was reachable as a linear combination of the first two vectors. So what is a nice word that describes this situation? We can say that these vectors were linearly dependent. There was a dependence among those three vectors in that one of them was expressible as a linear combination of the others, right? So this leads us to our definition, right? So in this, here, if you want to say what happened, well, this is the third vector was a linear combination of the first two, right? The way we say that is we say the vectors were linearly dependent. Right? So that's what happened here. And more generally, right, we can say that if you have some list of vectors, v1, v2, up to vn, right, that list of vectors is linearly dependent if and only if one can be written as a linear combination of the others. Right. So this is the definition of linearly dependent. I should mention this isn't, I think this is maybe the most intuitive definition. That's a perfectly valid definition. You'll often see it written in sort of a more formal way, which is to say, so I want to put that definition as well. So here's another condition that's equivalent to being linearly dependent. If you can take a linear combination of those vectors and end up with the zero vector. If you can do that, choosing at least one non-zero coefficient. You can't just, if you pick the zero, if you pick the number zero for C1, C2, all of them at the Cn, well, that's nothing special, right? That's not really saying anything. Of course, if you just pick zeros over and over again for your scalars, you get the zero vector. But if you can get the zero vector with at least one non-zero Ci, that's equivalent to being linearly dependent. How is that equivalent? Well, think of that previous example where we had that 3, 0, 1 was expressible as a linear combination of the other two, right? 1 times this one plus 1 times that one, right? Well, that, if you just throw everything on one side, that's the same as saying negative 1, 1, 0, 1 plus negative 1, 2, 0, 0 plus 1, 3, 0, 0 equals 0, 0, 0, right? So it's the same condition. saying that one vector can be written as a linear combination of the others is the same as saying that you can have a non-zero linear combination of your vectors to equal the zero vector. They're equivalent. Right? All right, so that's the idea of linearly dependent. Linearly independent just means not linearly dependent. Right? So that's those words. So that is up here, linearly dependent, linearly independent. Right? So those are our next few definitions. Um, why do we care about this idea? Well, here's the thing. There's the notion of a basis for a vector space. It's a list of vectors such that the vectors span your vector space V. So you have to have enough vectors to get all of V. But also, you can't have too many. You can't have redundant vectors in there. They have to be linearly independent, right? So the this definition of basis, right? It's like saying that the vectors v1 through vn span v is saying that there are enough to get v, right? But there's just enough, right? That's what the linearly independent says, that you have exactly enough vectors to span v, right? That's the idea of basis. So, for example, like what we saw up above, we would say that 1, 0, 1 and 2, 0, 0, right? This is a basis for the xz plane, right? So this is a basis for the xz plane because the span of those two vectors is the xz plane, and those two vectors are linearly independent, right? But if you said, this alone is not the basis for the xz plane, right? Why? Because it does not span, right? There's not enough there. 101 is a basis just for the really just the line x equals z in the xz plane, right? Um, and how about the other way? If we did all three of those vectors, right? That is not a basis for the xz plane. It does span, but it's not linearly dependent, right? That is linearly dependent, as we showed up above, right? So there's an example of a basis for the xz plane, and then two non-bases for the xz plane. All right. Why do we really care about basis? The dimension of a vector space is the number of basis vectors. Maybe a better way to say it is it's the number of vectors in a basis. Right, so this is the dimension of a vector space. It's not clear at all. It's not obvious that this is well defined, right? You can pick different bases. For example, I can pick the elementary basis for xz plane, I can pick the elementary basis vectors j and sorry I and k, right? So 1, 0, 0, and then 0, 0, 1. I can pick those two vectors. That's a different basis for the xz plane. But there are still exactly two vectors either way, right? So it's not clear that a different basis always has to have the same number of basis vectors, but it turns out to be true for vector spaces. So this is something very special about vector spaces. So that is our last little pair of definitions, right? So basis just means linearly independent and spanning, right? And then dimension is just number, right? Just how many vectors constitute a basis for that particular vector space. So this gives you a way to measure the size of a vector space, right? As opposed to just saying infinity, right? How many vectors are in R2 infinitely many? How many vectors are in R3 infinitely many? But this gives you a way to quantify that R3 is bigger than R2, right? R3 is a three-dimensional vector space because you'd have I, j, k. You'd have three vectors in a basis for R3. R2 is a two-dimensional vector space because you only need I and j to generate it, right? Or like say here, right? Our example here that we were playing with, right? The xz plane, right, is a vector space of dimension 2. And why is it a vector space of dimension 2? Well, because like we say, it's the number of vectors in a basis. So why is it dimension 2? Well, you just count them up. 1, 2. There are two vectors in that basis. That's why the xz plane is a vector space of dimension 2. So there we go. There's a definition of dimension, right, of a vector space. Dimension, it turns out in almost any context, dimension is a hard word to define, and this is no exception. If you look at this giant list of words that we have, all of those words are there basically to build up to the definition of dimension. You have to define all of those terms to get the dimension. So, all right. So there is a hard to define word, super useful dimension. See you next time.